Hello, and welcome. In this video, we will explore two key concepts in vector applications that are essential for the IB mathematics analysis and approaches higher-level curriculum. By the end of this session, you will be able to determine the shortest distance from a point to a line in both 2 and 3 dimensions, and you will be able to solve problems involving the motion of objects using vectors. These skills are fundamental for understanding and modeling real-world scenarios, from navigation to physics. Let's begin with our first objective, finding the shortest distance from a point to a line. Imagine a ship sailing along a straight path, represented by a line, and a port located at a single point. The ship's captain wants to know the closest the ship will get to the port. Visually, the shortest distance is always the perpendicular distance. This means the line segment connecting the point to the line must form a right angle with the line. Let's formalize this. Suppose we have a line L and a point P not on the line. Let R be any point on the line L. The distance between P and R is minimized when the vector PR is perpendicular to the line L. In vector terms, this means the vector PR must be perpendicular to the direction vector of the line. If the line L has a direction vector B, then the dot product of P, R, and B must be 0. This is the key condition we will use to solve these problems. The point R that satisfies this condition is called the foot of the perpendicular from P to the line L. Once we find this point R, the shortest distance is simply the magnitude of the vector PR. Let's work through an example in 2 dimensions to see how this method is applied. Consider a line with the vector equation R equals the vector 1, 2, plus t times the vector 3, negative 1. We want to find the shortest distance from the point P with coordinates 5, negative 1, to this line. First, let's identify the key components. The position vector of a point on the line is given by the expression 1 plus 3t, 2 minus t. The direction vector of the line is 3, negative 1. Let's call the foot of the perpendicular n. The coordinates of n can be written in terms of the parameter t as 1 plus 3t, 2 minus t. The coordinates of our point P are 5, negative 1. Next, we need to find the vector Pn, which connects the point P to the point n on the line. We calculate Pn by subtracting the position vector of P from the position vector of n. This gives us the vector 3t minus 4, 3 minus t. Now, we apply our key condition. The vector Pn must be perpendicular to the direction vector of the line. The dot product of Pn and the direction vector, 3, negative 1, must be 0. This gives us the equation 3 times the quantity 3t minus 4 minus 1 times the quantity 3 minus t equals 0. Let's solve this equation for t. Expanding the equation, we get 9t minus 12 minus 3 plus t equals 0. Combining like terms, we have 10t equals 15. Therefore, t equals 3 over 2. This value of t corresponds to the point n on the line that is closest to P. To find the shortest distance, we need to find the magnitude of the vector Pn at this specific value of t. Substituting t equals 3 over 2 back into our expression for Pn, we get the vector 1/2, 3/2. Finally, we calculate the magnitude of this vector. The magnitude of Pn is the square root of 1/2 squared plus 3/2 squared, which simplifies to the square root of 10 over 2. This is the shortest distance from point P to the line. The same principle applies in 3 dimensions. Let's look at a 3D example. We want to find the shortest distance from the point P with coordinates negative 1, 2, 3 to the line with parametric equations x equals 1 plus 2t, y equals negative 4 plus 3t, and z equals 3 plus t. First, let's write the line in vector form. The position vector of a point on the line is 1 plus 2t, negative 4 plus 3t, 3 plus t. The direction vector of the line is 2, 3, 1. Let's call the foot of the perpendicular A. The coordinates of A are 1 plus 2t, negative 4 plus 3t, 3 plus t. The coordinates of our point P are negative 1, 2, 3. Next, we find the vector PA. Subtracting the position vector of P from A, we get the vector 2 plus 2t, negative 6 plus 3t, comma t. Now we apply the perpendicularity condition. The dot product of PA and the direction vector, 2, 3, 1, must be 0. This gives us the equation 2 times the quantity 2 plus 2t plus 3 times the quantity negative 6 plus 3t plus 1 times t equals 0. Let's solve for t. Expanding the equation, we get 4 plus 4t minus 18 plus 9t plus t equals 0. Combining like terms, we have 14t equals 14. Therefore, t equals 1. This value of t gives us the foot of the perpendicular, a. Substituting t equals 1 back into the coordinates for a, we find that the foot of the perpendicular is the point 3, negative 1, 4. To find the shortest distance, we calculate the magnitude of the vector PA at t equals 1. Substituting t equals 1 into our expression for PA, we get the vector 4, negative 3, 1. The magnitude of this vector is the square root of 4 squared plus negative 3 squared plus 1 squared, which is the square root of 26. This is the shortest distance. Now let's move on to our second objective, solving problems involving the motion of objects using vectors. In these problems, we use vectors to describe the position, velocity, and path of moving objects. The fundamental equation for motion with constant velocity is the position vector at time t, r of t, is equal to the initial position vector r naught, plus the time t multiplied by the velocity vector v. Let's break this down. R of t is the position of the object at any time, t. R naught is the starting position of the object, and v is the constant velocity vector, which tells us both the speed and the direction of motion. A common type of problem involves finding the time when an object is closest to a fixed point, like a port or a control tower. This is essentially the same shortest distance problem we just solved, but with a time-dependent position vector. Let's consider an object moving along a path described by r of t and a fixed point p. We want to find the time t when the distance between the object and p is minimized. The vector connecting the fixed point p to the object at time t is r of t minus p. For the distance to be shortest, this vector must be perpendicular to the object's path, which is in the direction of its velocity vector v. So, the condition is that the dot product of the vector r of t minus p and the velocity vector v must be 0. Solving this equation for t will give us the time of closest approach. Let's apply this to a problem involving a helicopter. A helicopter is at point A, 6, 9, 3. 10 minutes later, it is at point B, 3, 10, 2.5. We need to find its speed, its path, and the time it takes to land at a helipad with a z-coordinate of 0. First, let's find the displacement vector from A to B. The vector AB is found by subtracting the position vector of A from B, which gives us negative 3, 1, negative 0.5. Next, we find the helicopter's speed. Speed is the magnitude of the displacement divided by time. The magnitude of AB is the square root of negative 3 squared plus 1 squared plus negative 0.5 squared, which is the square root of 10.25. The time is 10 minutes or 1/6 of an hour, so the speed is the square root of 10.25 divided by 1/6, which is approximately 1.92 kilometers per minute, or 115.2 kilometers per hour. Now let's determine the vector equation for the helicopter's path. We use the formula r of t equals r naught plus t versus. We can use point A as our initial position, r naught. The velocity vector v is the displacement vector AB divided by the time, which is negative 18, 6, negative 3. So the path is r of t equals 6, 9, 3 plus t times negative 18, 6, negative 3. Finally, we find the total time to land at a helipad with a z-coordinate of 0. The z-component of our position vector is 3 minus 3t. We set this equal to 0 and solve for t. This gives us t equals 1 hour. This is the time from point A. Since the helicopter was at A after 10 minutes, the total time from its starting point is 1 hour and 10 minutes. Let's tackle another motion problem, this time involving a ship in a port. An ocean liner is at position 6, -6, and is cruising at 10 kilometers per hour in the direction -3, 4. The fishing boat is anchored at the origin, 0, 0. We need to find the time and position of the liner when it is nearest to the fishing boat. First, let's find the velocity vector of the liner. The velocity vector is the speed multiplied by the unit vector in the direction of motion. The unit vector is -3, 4, divided by its magnitude, which is 5. So the velocity vector is 10 times -3/5, 4/5, which simplifies to -6, 8. Now we can write the position vector of the liner at time t. Using the formula r of t equals r0 plus tv, we get r of t equals 6, -6, plus t times -6, 8. The fishing boat is at the origin, p equals 0, 0. We need to find the time t when the liner is closest to the boat. We use our perpendicularity condition, the dot product of the vector from the boat to the liner, r of t minus p, and the velocity vector v must be 0. Since p is the origin, this simplifies to r of t dot v equals 0. Let's solve this equation for t. The dot product is 6 minus 6t, -6 plus 8t, dot -6, 8. This gives us -36 plus 36t minus 48 plus 64t equals 0. Combining terms, we get 100t equals 84, so t equals 0.84 hours. This is the time of closest approach. To find the position at this time, we substitute t back into the position vector equation. Substituting t equals 0.84, we find the position vector is 1.92, 0.72. This is the position of the liner when it is closest to the fishing boat. Let's recap what we've learned today. We've covered 2 essential vector applications. First, we learned how to find the shortest distance from a point to a line by using the condition that the vector connecting the point to the line must be perpendicular to the line's direction vector. Second, we applied this same principle to solve motion problems, finding the time and position of closest approach for a moving object. These methods are powerful and versatile, allowing us to solve a wide range of problems in geometry and kinematics. Mastering them is crucial for success in the IBAAHL course. To help you solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try to solve them on your own before looking at the solutions. Question 1 asks for the shortest distance from a point to a line in 2 dimensions. Question 2 is a similar problem in 3 dimensions. Question 3 involves finding the foot of the perpendicular. Question 4 is a motion problem with a ship and a port. And question 5 is a more complex motion problem involving an aircraft and a radar screen. Let's go through the solutions. For question 1, the shortest distance is the square root of 5 over 2. The solution involves setting up the vector Pn, taking its dot product with the direction vector 1, 2, and solving for t. This gives t equals -1/2. Substituting this back into Pn gives the vector -3/2, -1. The magnitude is the square root of 5 over 2. For question 2, the shortest distance is the square root of 26 over 2. The process is identical to the 3D example we did earlier. We find the vector PA, dot it with the direction vector 2, 3, 1, and solve for t. This gives t equals 1/2. The magnitude of PA at this t is the square root of 26 over 2. For question 3, the foot of the perpendicular is the point 5, 1, 5. We find the vector PA, dot it with the direction vector 3, 2, 1, and solve for t. This gives t equals 1. Substituting t equals 1 into the line's parametric equations gives the coordinates of the foot of the perpendicular. For question 4, the liner is due east of the fishing boat after 0.75 hours. Due east means the y-coordinate is 0. We set the y-component of the position vector, -6 plus 8t, equal to 0, and solve for t. This gives t equals 3/4 of an hour. And for question 5, we can show the aircraft is visible at 1 p.m. First, we find the velocity vector and the position vector r of t. At 1 p.m., t equals 1 hour. We find the position vector at t equals 1, which is -100, 0. The distance from the origin is the magnitude of this vector, which is 100. Since this is within the 100-kilometer radar range, the aircraft is visible. Thank you for watching. I hope this video has provided a clear and rigorous explanation of these important vector applications. Keep practicing these types of problems to build your confidence and mastery for the IB DAHL exam.